Consider two objects. One is hot, the other one is cold. And put them in contact. What's going to happen? So hot object cool downs and cold object warms up, and they will reach thermal equilibrium. The temperature of hot object and cold object will be the same. So energy transfer takes place between the two objects. So how much heat is transferred? That is Q. So heat is transferred from the hot medium to the cold medium. Here is a sign convention for heat. So when the heat is transferred to the system, it is positive. When the heat is removed from the system, it is negative. So if we take the system in hot object, heat is transferred from the system. So Q is out. So Q is negative. If we take system around the cold body, heat is transferred to the system. So Q is positive. Remember, the sign convention for work was exactly the opposite. Heat is denoted by Q when it represents the amount of energy transferred by heat. So heat is the transfer of energy. So it has the unit of energy, joule, same as work. So SI unit for heat is joule. English unit is BTU, or pound, feet times pound force. Heat is denoted by Q dot when it represents the rate of heat transfer. The unit is watt, joule per second, or BTU per hour. Heat is denoted by lowercase q dot when it refers to heat flux, or the rate of heat transfer per unit area. So we can also write it Q dot over A. A is the heat transfer area. Unit is watt per meter squared, or BTU per hour per feet squared. There is no standard notation for heat, but this is what we are going to use in this class. Also, when you see Q with the subscript 1, 2, represent the amount of heat transfer during the process between the state 1 and state 2. Can you define Q1 or Q2? No. Heat is not defined at a state. Heat is only defined between the states, just like work. Here is new term we often use in thermodynamics, adiabatic. So no heat is transferred in or out of the system during an adiabatic process. So if the system is perfectly insulated, Q so heat cannot go in or out of the system. So Q equals 0. So if a system undergoes an adiabatic process, it experiences no heat transfer between the system and the surroundings. So even if there is a temperature difference between the system and surroundings, no heat can be transferred across the boundaries. So is there another way to transfer energy to the adiabatic system? Yes, through work. So energy can be transferred by work. It can change the energy in the adiabatic system. For example, in the previous class we learned paddle wheel work. So if there's a paddle wheel connected to the system across the system boundaries, it can add energy to the system. Let's find out the modes of heat transfer. Heat transfer occurs because of a temperature difference, and the temperature difference is the driving force for heat transfer. So heat transfer is always from the higher temperature medium to the lower temperature medium. And the heat transfer stops when the two mediums reach the same temperature. There are three basic mechanisms of heat transfer: conduction, convection, and radiation. So let's first look at conduction. Conduction is the transfer of energy from the more energetic particles of a substance to the adjacent, less energetic ones as a result of interactions between the particles. So conduction can occur in solids, liquids, and gases. So consider a plane wall. So this is the cross-sectional view of the plane wall. It has a thickness L. The temperature on the left surface T1, temperature on the right surface T2, and T1 is greater than T2. So what is the direction of the heat transfer? Heat transfer always occurs from a higher temperature to the lower temperature medium. So higher temperature, T1 is higher than T2, so heat transfer from left to right. Experimental observations shows that the rate of heat transfer, Q dot, is proportional to the heat transfer area. Rate of heat transfer is proportional to the heat transfer area. The larger the heat transfer area, the more heat can conduct through a medium. The rate of heat transfer is also proportional to the temperature difference, delta T. In this case, T1 minus T2. So the larger the temperature gradient, the higher the heat transfer rate through the medium. Rate of heat transfer is inversely proportional to the distance the heat travels. So combining all these observations, we come up with an equation called Fourier's law of heat conduction. So Q dot, we can write Q dot is proportional to A delta T over L. So Fourier's law of heat conduction is based on experimental observations. K is the thermal conductivity. It is a material property. The higher the thermal conductivity, the better conductor. Typically metals are better conductor than non-metal. So metals such as aluminum, copper are good conductor. And styrofoam and fiberglass are good insulator. They are poor conductor. Negative sign is added to make Q dot positive in increasing x directions. dt over dx temperature gradient is negative. To make Q dot positive, negative sign was added. Convection is the mode of heat transfer between a solid surface and the adjacent liquid or gas that is in motion. Consider a plate with a temperature Ts, and fluid is flowing across the plate with a temperature T infinity, velocity U infinity. So there is a temperature difference between the adjacent fluid and the solid surface. So there will be heat transfer from the plate to the surrounding if the surface temperature of the solid is greater than the surrounding fluid. So heat transfer from the plate to the surrounding. Newton's law of cooling states that the rate of heat transfer is proportional to the temperature difference between the solid surface and the adjacent fluid that is in motion. So it is also proportional to the heat transfer area, A. Newton's law of cooling is also based on experimental observations. H is the convection heat transfer coefficient. It is not a material property. It depends on many variables, including fluid velocity, fluid property, fluid types, and etc. So it is experimentally determined. Radiation is the energy emitted by matter in the form of electromagnetic waves or photons as a result of the changes in the electronic configurations of the atoms or molecules. Radiation is emitted by solids, liquids, and gases, and radiation emitted through vacuum. Radiation does not require transport medium. Radiation emitted from the sun and travels through the vacuum of space and receive the solar energy at the surface of the earth. Radiation in thermodynamics refers to thermal radiations, only including infrared radiations, visible light, and a portion of ultraviolet radiation. Stefan Boltzmann's law states the emitted radiation, here Q dot, emitted radiation from a surface is proportional to the emissivity, epsilon, and surface area, A. It is also proportional to the force power of its absolute temperature. Sigma is a Stefan Boltzmann constant, and emissivity is the radiation property ranging between 0 and 1. Radiation emits in all directions, and all metals above 0 Kelvin emits radiation. So our body emits radiations, the wall in your room, your desk, everything above 0 Kelvin emits thermal radiation. In heat transfer class Mean 461, you will study in depth about conduction, convection, and radiations. In this class, just remember the three modes of heat transfer and the basic principles of each heat transfer mechanism. The heat Q may be transferred by one of the heat transfer mechanisms or combined modes of heat transfer.